of today's lecture, and we will use these notes as our guide. So what is a continuous random variable? It is a random variable which, in contrast to what you have seen so far, the discrete random variables, the range of values is continuous, doesn't have any gaps. It doesn't have any gaps between values. So for any two values, essentially you can find all sorts of other values in between. A typical example might be temperature. The temperature may be, it's a real number. Of course, you don't have an infinite, huge accuracy in the thermometer. You have 1 or 2 degrees, 1, 2 decimal points, the most, but still that variable, that random variable, can be modeled as a continuous random variable because this is what it is. I mean, light intensity, chemical quantities like pH concentration, blood serum concentrations of different things. Those are all continuous examples of continuous random variables. So to simplify life, we use it's no, it's not in Dropbox. I'm just using something magnified. Yeah, it's magnified. So what exactly we want now to see is what's the range of the random variable. So you can simplify it and always take that the range of a continuous random variable is from negative infinity to infinity. And let the probability density, the probability model, to take into to consider which values are likely and which values are not likely. So to understand which values are likely and which values are less likely, we use what we used also in discrete random variables, the density function. But this time the density function is defined on the entire real line. It's not defined at points, and the values of the density function do not represent probability. They just represent a rate at which the probability changes. They represent density of the probability. Okay? You will see that. So f of x, and I also need to write. So when we say f of x, this is not probability value. This is not a value representing probability. I will post these notes so you don't need to keep notes. Okay? The printed part. What is the other basic property? The other basic property is that, of course, f of x, the density function, takes non-negative values, and if you integrate that function from negative infinity to infinity, the integral is equal to 1. We've seen this property before. We've seen it in the form of the summation. So for discrete random variables, what we had was that if you sum the density over when x ranges over all values of x, over all values of x, this is equal to 1. Well, for continuous random variables, we have the corresponding property, but now since the range is continuous, doesn't have any gaps, we can no longer use a sum, we have to use the integral. And since the range extends from negative infinity to infinity, it's the entire real line, then if we integrate the density function over all the range of the values of the random variable, we should get equal to 1. So those two are essentially different phases, different different examples of the same property, that density, probability density integrates to 1. So those are the basic properties for the density function. Now, what is the definition of the density function? So if x is a continuous random variable, a function f which is non-negative and the integral is equal to 1 is the density of x if the probability that x takes values between a and b is equal to the definite integral of the density function from a to b. So this is the key formula that defines what density is. And it tells us how to use density to calculate probabilities. There is another fundamental difference with discrete random variables. With discrete random variables, then the probability that x takes a certain value can be positive. Here, for continuous random variables, the probability that x takes a certain value, a fixed value, not a certain value, not a fixed value, a certain value is always equal to 0. I mean, how can you ever hit temperature, let's say, with accuracy, with non-restricted accuracy? There's no way. The higher the accuracy you want, the bigger the uncertainty of your measurement. Therefore, the probability that observing one specific value of temperature is actually equal to 0. So there is no probability concentrated on certain values. And this is a very big difference from what we used to have for discrete random variables, where for discrete random variables, for every value of the random variable, the probability was either 0, so you could exclude that value, or it was actually positive, so that value had something, some contribution there. Could appear with some likelihood. Here, a value cannot appear with any likelihood, and therefore, only continuous ranges of values can be realizable events with some probabilities. And in fact, all of these events all have the same probability. So no matter how you treat the endpoints of the integral, what kind of inequalities you use here, always these probabilities are going to be equal to the integral of the density function from a to b. Okay? And that follows precisely from the fact that for continuous random variables we have this property. No probability. It's impossible to get a specific value. You can get a range of values, and that range can be up to the accuracy of your instruments, but you cannot get a specific value. In other words, you cannot have infinitesimal accuracy. The likelihood of the occurrence of infinitesimal accuracy is 0. Can happen, yes. Really close means accuracy. No, you mean the value, the probability? No, it's 0, mathematically 0. And it's because it follows from these equations. You see, the probability, this is the fundamental equation which connects probability with the density function for continuous random variables. So the probability that x takes the value a is the probability that a takes values from a to a, which means that then you would integrate from a to a the density function. But when the length of integration has length 0, the interval of integration has length 0, the integral is equal to 0. Yes.
So let's say that there's a number c in between a and b. Would the probability that x equals c be 0?
Didn't get that? I think at that point it's better if I give you an example, which is the so-called uniform distribution. And actually can go to, first I can remind you one thing. Do you remember when I write the integral from negative infinity to infinity, this is called the generalized integral, and that integral is the limit when a and b go to a, the minus a goes to negative infinity, b goes to plus infinity of f of x. So it's a limit of definite integrals. That's a generalized integral, as we call it. And after you calculate that, then you can find the limit, and you have it. Now you can take the limit with both a and b equal, being the same thing, a equal b. That actually makes it easier in the calculation. You don't have something that you need to worry about. So now let's look at one specific case. This function, this density, which is equal to 1, if you have two numbers, two real numbers, a and b, and the density is equal to 1 over b minus a, when x is between a and b and it's 0 outside, it's called the uniform distribution in the interval from a to b. And practically the uniform distribution is saying that any range of values which has a specific length between a and b is equally likely. So in other words, this random variable can return any number equally likely, loosely speaking, between a and b. But you are not going to observe any values. That's super unlikely that you will observe any values outside of a and b. So it's the uniform probability, the uniform distribution. Okay? So let's see, let's play a little bit with the uniform distribution. Let's try to understand it and illustrate the concept. And to do this, I will do the uniform distribution in the interval from 0 to 1. So I have a random variable x, which takes real values, any real value. And I'm saying that the density of x is 1 if between 0 and 1, and 0 outside. What is the probability that x will take values which are, let's apply our rules, the rules that we've set, between negative 10 and negative 1? Actually, negative 0.72. Let's put that. Well, according to what we have here, that would be the integral of the density function between the endpoints. Okay, so that would be the integral from negative 0.70, from negative 10 actually. I mean the negative half axis, so numbers go the opposite way. This is what determines the probability. And now, what is the value of f outside 0 and 1? That's 0. So essentially you integrate 0 because the interval of integration does not overlap with 1, 0, 1. So you integrate the value 0, so the integral, as everybody can see, will be equal to 0. So it's super unlikely that the random variable will take any values between -10 and -0.72. Likewise, it will be highly unlikely that it will take values in any interval of the form when b is greater than 1. Alright? Even if b is greater than or equal than 1, still it would be the same because that quantity would be, if I do this, still the integral will be from b to c. But even if b is equal to 1, so in this case you would have had this, over there still the value is equal to 0, except at one point at 1. But this would make the integral equal to 0, and you can see that if you start from 1 all the way to c, the function is equal to 0, even to 1, but then all the remaining values are 0. So the area under the integral, under the curve, under the graph of the function f, of the density function, is nothing, is 0. Because the graph is this point, and this straight line here is flat, right on the x-axis, doesn't have any height. So there is no area there. Okay? So that's this integration. Now, I understand that sometimes you have trouble integrating when you have a jump discontinuity. If you have a jump discontinuity like this, suppose that I had to integrate to find the probability that x takes values between 1/2 and 10. Let's say that we have that. The uniform x is uniformly distributed as before. And that would have been the integral from 1/2 all the way to 10 f of x dx. Now, what is the point where f changes value? The point where f changes value is at 1, this point. So I will break my integral from 1/2 to 1, and then I will go from 1 to 10. What is the value of f here in this interval from 1/2 to 1? Well, it's 1. So I integrate 1/2 to 1 times dx. In the other part, except only for one point, for a single point, the value of the density function is equal to 0. So that will give you 1/2, and the second term will give you 0, so it's 50%. All right? Is it clear? How many calculation? Any questions? The distribution function of f. What we call CDF, the cumulative distribution function of x, or simply the distribution function of x. Hence the term distribution. The definition is exactly the same as we did for discrete random variables. So the cumulative distribution function of x, which again I denote with f, but I use the capital sign, is defined for every a positive, a real, so it takes this a to be real, and it's the integral from negative infinity to a of the density. So if I look at it graphically, this is the axis of negative infinity to plus infinity. You expect to see something like that. If this is A, this integral, actually this area under the graph, is the function of f of x at this point, the distribution function at this point. And this is nothing else but the probability that x takes values less than or equal than A. So exactly it's this condition we use to define the density function, the distribution function. And we show this condition again for discrete random variables. So in other words, discrete random variables and the distribution functions for discrete random variables and for continuous random variables have exactly the same definition. There's no difference. And that's a unifying property. What is the proper definition of a continuous random variable? Its range of values is continuous and its density or excuse me, its distribution function is continuous and differentiable. Differentiable everywhere except at a finite number of points. Questions so far? Okay, now let's look at some examples. Differentiable at a finite number of points. Well, let's do an example and we will see that. The example will illustrate this immediately. Let's go back to our x, which has uniform in the interval 0 to 1. So the density function has already been shown. Mm-hmm. So if we see, for example, let's say f of x of A is equal to 0 if A is negative, okay? And that's because if here is 0 and 1, and the density is with the red, the graph of the density. All right? So I have this. So if I integrate, if I have A here, let's say here is A, and I integrate left of A, that's the probability that x takes value less than or equal than A. So this is the integral, the generalized integral from negative infinity over to A. What is this equal to when x is less than a? It is 0. So I integrate the value, the constant function equal to 0, so that will give me 0. All right? Now let's look if a is between 0 and 1. Let's put a here. Let's keep the graph. So this is the integral from negative infinity all the way to a again of the density. But now we see that since a, here is a between 0 and 1, since a is between 0 and 1, for that part from 0 to a, the density is different, takes the value 1. So I break the integral in two parts, from negative infinity to 0, and from 0 to a. This part is going to be 0. What is this part going to be equal to? Here, the density between 0 and 1, or between 0 and a in particular, is going to be equal to 1. Because of the definition, we said that x has uniform distribution. So somewhere here we mentioned. Here's the formula. So that integral is going to be equal to 1 from 0 to a dx. So that will give me a. So now if we do the graph of the distribution function, we go here, then we go up to 1, and finally we reach 1, and we continue straight for sum. Now, when do I reach the value 1? When does the distribution function reach the value 1? Where does it reach the value 1? Yeah, but where does this area become equal to 1? Look here. That's the part will give you the answer. What? When a becomes 1, okay? So when a becomes 1, it reaches this value and stays fixed thereafter. Doesn't change. And here there's another property which is very important, a property of the distribution function, which says that the distribution function is a non-increasing function. It's not differentiable everywhere. As you see here, that point, here you have a sharp turn. There's this, as we call it, this pattern is piecewise linear. So it abruptly turns up and then abruptly flattens. These are the points where the function is not differentiable, but it's differentiable everywhere else. That's why the characteristic of continuous random variables is that their distribution function is continuous and differentiable except for a finite number of points. So it's not only the range, but also the property that the distribution functions have. And that's the proper definition. Now, another crucial thing that comes from this formula that we just mentioned, which is called, how is this formula called, essentially? Very well. The fundamental theorem of calculus. Very well. Thanks. That's a very good answer. This is the fundamental theorem of calculus. And that means what? And let's see, actually, let's expand this formula. And now it will look more like the fundamental theorem of calculus. Let's do a calculation. Let's squeeze a calculation here. The first calculation is for probabilities. So the probability of A of X being less than or equal than B. So if a value comes less than or equal than B, that value can be less than A or between A and B, correct? So if X is less than or equal than B, then it can be less than or equal than A, or it can be between A and B. So this means that this is the probability between A, X, B, plus the probability that X takes values less than or equal than A. Right? Now this integral, this probability here, is exactly equal to the probability that A is less than or equal than X, less than or equal than B, because we mentioned that the probability that X takes precisely the value A is equal to 0. So these two events should have the same probability, because what they differ is by just one particular value, X taking the value precisely A. But that's almost impossible. Probability is 0. Therefore, this calculation here that I have mentioned, that I have just done, shows that the probability of X less than or equal than B minus the probability X less than or equal than A is equal to this probability here. But what is this value? This is the value of the distribution function of X at B minus the value of the distribution function of X at A. And now if you look at the distribution function at the difference and you correlate that picture with the integral, this is precisely the fundamental theorem of calculus. So what does it say, the fundamental theorem of calculus? The fundamental theorem of calculus will say that if you differentiate the distribution function because of this equality, you will find the density function. So the relationship between CDF and density in in continuous random variables is the following. The derivative of the distribution function is equal to the density function, where the derivative exists. Do you understand the word differentiable, or should I turn the video off? Are you all familiar with the term differentiable? So, in summary of what we have done so far, this is one of the things that we need to keep, that the distribution function, if the cumulative distribution function is differentiable and we take the derivative, then we find the density function. That's a very useful property. And the second is the second fundamental theorem of calculus, which relates that the probability of A, X, B, all those probabilities are equal and all of them are equal to the value of the distribution function at x at b minus the value of the distribution function at a. And of course, this is the integral from a to b of the density function. I will continue with a very important notion, the notion of the quantiles. Actually, I want to mention something more general, the percentiles. So suppose that we have a number between 0 and 100. Let's give it a different notation. Let's call it L. X is a random variable, is a continuous random variable, but what we mentioned also apply for discrete random variables. So I will say just a random variable. And f sub x is the cumulative distribution function, or simply the distribution function of x. The real number p sub l, which is the solution of the equation equals L over 100, is called the L percentile of x. Now, if L is 25, then P sub L, or I will call it P25, is called, sometimes it's denoted as Q1, and it's called first quartile. For L equal 50, this number is called Q2, and it's called either second quartile or median. And for 75, when L is equal to 75, this number is called the third quartile. And when we use the term box plot or box and whisker plot, that's a very easy way to put these numbers. So in a box and whisker plot, we put the maximum and the minimum number, minimum value and maximum value. Typically, this is only asked when we have data, because if we don't have the data, but we consider the random variable in abstract, this minimum can be negative infinity, this maximum can be plus infinity. And then we plot the values. We put the box in a sense that here somewhere we'll put the Q2, the median. Here we put Q3, and here we put Q1. And the straight line is the range of real numbers, range of values here. That's what it depicts. Now, to close this presentation, I would like to work on some problems. So let's look at some of the problems here in the book. I will look at the first problem now. Problem number 1. We have a circuit and the current in a certain circuit is measured in some unit of measurement, and it's a continuous random variable with this density function. So we're given the density function, the PDF. First of all, the first question is graph the PDF and verify that the total area under the density curve is indeed equal to 1. Let's see. Something that probably I did not mention, the graphical interpretation, is that if we have the PDF of the function, so this is the x-axis here, and this is the PDF of the function. Let's say that it looks like this. The area under the PDF, the entire area under the PDF, represents the probability that the value that x will take any particular value, so it should be equal to 1. So this area now is the area that represents this event, and therefore this should be equal to 1 because the random variable will take one value, and this value is going to be greater than negative infinity and less than plus infinity. So that's a universal event. It's nothing too specific, and therefore its probability should be equal to 100%. If we want to specialize a little bit, and now let me solve this kind of PDF. Let's say that I have something like this, and here is my B, and here is my A. This area here under the curve, this is the graph of the PDF. This area represents the probability that A is between A and B. And of course, as I mentioned, all those probabilities here are the same. So it doesn't matter whether you have those inequalities closed or less than or equal or strictly less, always the probability is equal to the same thing. Now, I showed you this equation. Let's look at the very last equation. How the very last equation is interpreted in terms of the graph of the PDF. So I'm drawing again the same, roughly the same curve. It didn't come out to be exactly the same. Let's say B is here and A is here. This area, my green area here, the green area represents what? Let's see the range here of the values of x. So on the horizontal axis we have values of x. The values of x here are are not greater than b, are less than or equal than b. So that implies that the green area is the probability that x is less than or equal than b, and of course this is equal to the value of the distribution function of x at b. Likewise, if I make the cut at a, the values of the blue area now probably we need to get a different color. The values of this purple bluish area. So purple area is equal now to the probability that x is less than or equal than a, and this is the value of the distribution function at a. So the difference between the two is precisely the probability, it's this probability, and that's the graphical interpretation of the equation that we used as a result of the second fundamental theorem of calculus, which was summarized here. This is a very, very important identity which I would like you to remember. This is the main summary of what we had to cover today. Keep those graphs for future reference. Now let's go to problem 1 again. And with problem 1 we have this function here. Now we want to, we will graph the PDF. Let's try to graph the PDF. F of x is equal to so the graph of f of the PDF of f should be like this. Here is 0. Let's say here is 3. Here is 5. And let's do the graph with the red line. When we first hit 3, we immediately jump to point 2. And then the curve continues straight on. And here I anticipate that I will take a certain value, which is equal to 1. And further on, from that point on, it goes down to, or some value there. It's not equal to 1. It's not a CDF. It's the PDF. It goes to 0. So that's the graph here. It falls down to 0. So this gap is 0.2. Let's see what is this gap here. Of course, this gap at 5, f of 5, is 0.075 times 5 plus 0.2, and this is equal 575. So this gap now is 0.575. The problem is asking us to verify that this area under the curve, and the curve now is a straight line, is equal to 1. Well, this is a trapezoid here, so but you can also use what we have mentioned so far. So we need to integrate f of x dx from negative infinity to plus infinity. Now this function, the density function, is 0 outside of 3 to 5, so this integral collapses to the integral from 3 to 5 of f of x dx, and between 3 and 5 this function is linear, so you have to integrate 0.075 times x plus 0.2 dx from 3 to 5, and this is going to be 0.075 times 5 minus 3 square over 2. That comes from the first term, and the second term is a constant 0.2 times 5 minus 3. So if we put all these together, then we find that this is equal to 1 if you do the calculation. Now let's work at question number 2 of the problem. Calculate the probability of p less than or equal than 4. How does this probability compare with p less than x less than 4? Strictly, they are exactly the same, and we mentioned that because the probability that x is equal to 4 is equal to 0. Okay, why is this 0? Because you would integrate from 4 to 4 the density function, and when you integrate a function over an interval of length 0, that gives you 0. So what is the probability of x less than or equal than 4? This is the integral from negative infinity all the way to 4 of the density function. You always begin with the density function, and then you do after you have the integral, then you do the replacements. Now you break the integral at 3. And then you go from 3 to 4. The function is 0 between negative infinity and 3. And between 3 and 4, it takes the value we have used before. So this is going to be 0.075, 4 minus 3 squared divided by 2 times 0.2, 4 minus 3. And this is the result. This is exactly the probability we need to calculate. You do the math, and that gives the problem. That gives the answer to the problem. And if we want to do question C, then we can calculate the probability between 3.5 and 4.5. So the probability between that x takes values between 3.5 and 4.5. That would be the integral from 3.5 to 4.5. Always put f of x dx and then do the replacements. 3.5 and 4.5 are between 3 and 5. So I can immediately replace the function with what I have been given, and do this calculation. Now, if for example, you had to calculate the probability that x is between 3.5 and 6.2, since 6.2 is greater than 5, it falls outside of the interval 3 to 5. It's somewhere like here, somewhere here. That's where 6.2 would be, let's say. Then I have to break the integral in two parts. The one between 3.5 and 5, and the other from 5 to 6.2. Well, that would be now I'll break it up to 5, and then from 5 to 6.2. But here, in this interval between 5 and 6.2, the density is 0, so that would have been the integral from 3.5 to 5 f of x dx. And now you do the math, the rest is easy. Let's stay with this example and let's calculate the cumulative distribution function. First, we begin with values when a is less than 3. Actually, we can say less, let's go strictly less than 3. That would be the integral from negative infinity all the way to a, f of x dx. Let's graph the function again so we can have some perspective. So here is 3, here is 5, and that's the graph of the PDF graph. The red line should be the graph of the PDF. If a is here, then you understand that this is 0. So in this case, the whole integral should be equal to 0. Now let's look at f sub x of 3. This would be the integral from negative infinity to 3 f of x dx. But now at 3, the density function takes a value, takes a positive value. So how can I do this integration? Well, what I will do is to break this integration into two parts. Put a fictional number c, which I would put it to be close to 3, and integrate up to that point, and then continue from c to 3, f of x dx. Now this integral is equal to 0, so the integral that remains, the first integral is equal to 0 because f is 0 between, the density function is 0 between negative infinity and c, because c is strictly less than 3. The other is from c to 3, so what remains is this. Obviously, since f of x is greater than or equal than 0, always this value is expected to be greater than or equal than 0. As we have seen so far, this is equal from the integral from c to 3 over f of x dx. And this integral is less than or equal than the value of f at 3, because that's when the function at first jumps to a positive value. This positive value is 0.2. So f of x is less than or equal than 0.2 for all x less than or equal than 3. So I'm using this inequality times the length of the interval from c minus 3. This is true for every c. This inequality now that I have here. So you see I sandwich this integral between 0 and this upper bound. And these inequalities are true for all c less than 3. Now take the limit of the right hand side when c goes to 3 from the left. Then this quantity goes to 0. And as you understand, all of this goes to 0. But that number doesn't change because it doesn't depend on this limit. What depends on the limit on C is the right-hand side. Therefore, the integral I wanted to calculate is sandwiched between 0 and 0, and therefore it has to be 0. And the moral of the story is that what counts for the integration is the values on the entire interval up to 3. The fact that the function jumps to a positive value at 3, which is the end point of the integration, or just one point in the interval of the integration, doesn't really count, doesn't change the result of the integration, because that positive value does not occur at an interval with positive length, but it occurs at just one point, which means it occurs at an interval with 0 length. This explains exactly this calculation that I've done here qualitatively. Quantitatively, formally, this is the right calculation. Now let's take A to be between 3 and 5. All the way up to 5. We can go all the way up to 5. Now we have f of x of a. This is the integral again from negative infinity to a. So now I'm breaking this integral into two parts, from negative infinity all the way to 3. And now from 3 to a. What is the first integral here? The first integral is the value of the distribution function at 3, which I calculated, and this value is equal to 0. This is what I did precisely. Look at this integral here. So what I'm left with is the value, is the integral from 3 to a. And we've done the calculation before. We did it, I think, for 4. So this is nothing else from 3 to a of the function. The function, the density function, takes the value 0.075 times x plus 0.2 dx. So this is, if we do the integration, a minus 3 I realized that I was doing some wrong calculation all the way up. No, this is 4 squared minus 3 squared. And I did it several times. Excuse me. And I did it here one more time. So let me correct it. Small errors in the calculations. A squared minus 3 squared plus, I'll divide it by 2, plus 0.2 times a minus 3. So that's the result there. In f of x, when a is greater than 5, that is equal to, since a now is greater than 5, that would be the integral from a negative infinity to a, as we did before. Now break the integral from negative infinity to 5, and from negative infinity to, from 5 to plus infinity. Now if you see, this integral is equal to 1, because that's the value of the distribution function at 5. this integral is equal to 0 because f is equal to 0 when f is greater than 5, when x is greater than 5. We're talking about these parts. Therefore, this is equal to 1, which is the value of the distribution function at 5. Once the distribution function reaches the value 1, it stays there, it cannot go up. Here is a summary of the properties of the values of summary of properties of CDF. We don't need all of those properties, so I will summarize the main ones. That's true for all CDFs. And it's valid also for CDFs of discrete random variables. All values are between 0 and 1. The limit of the value of the CDF when a goes to negative infinity is 0. The limit of the CDF when a goes to plus infinity is equal to 1. And f of x is non-decreasing. So it always either goes up or stays flat, but it never goes down. That's why when you reach the value 1, for every other point as it was here, a greater than 5, you don't have to worry what the value of the CDF is going to be. This value will stay equal to 1. I would like to do a calculation now for this problem since we have the CDF. Let's summarize the CDF. Let's use A. So this is the CDF of X. Now we'll use this CDF, that's the summary, that's what we calculated here in the previous part. Now I want to find what is the value of the CDF, what are the percentiles. So let's say that we want to find the 50th percentile or the median. So what would be this? We want to solve the equation FP50 so that this is 50 over 100. That's the definition of the 50th percentile. So this is equal to 0.5. So we look at these branches here. Obviously, this number cannot be less than 3. Cannot be greater than 5 because once you have a greater than 5, then the value of the CDF is equal to 1. So it has to be between 3 and 5. So we'll pick the solution from the mid branch, from this branch here. So we need to have 0.75 a squared minus 3 squared, actually 250 that should be equal to 0.5. This is a quadratic equation. We can straighten it up a little bit. And it's 0.075 250 square plus 0.4 250. And then if we do all the other calculations, we'll have 1 plus 1.2, everything goes to the right hand side, plus 9 times 0.075, and that's the equation, that's the quadratic equation we need to solve. This quadratic equation has two solutions, but you keep the solution that is between 3 and 5. Why? Because that 3 and 5 comes from this constraint. The 50th percentile, the median, cannot be greater than 5, cannot be less than 3, because had it been less than 3, you understand, the value that the distribution function would take would be equal to 0 and not equal to 0.5. And had it been greater than 5, the value of the CDF would have been equal to 1. So that doesn't qualify as well. And that would be the solution of the problem. In this one, because the CDF has a very beautiful, very simple form, the graph is the area that it cuts. It's a trapezoidal area. Then it's easy to understand where to put the value here, where to put a line so that this is equal to 1/2 and this is equal to 1/2, because the entire area of the trapezoidal should be equal to 1. So that is something that, of course, it doesn't go in the middle, because the trapezoidal is flatter, is wider here than it is here. It goes somewhere else, but I think you can verify that doing a little bit of geometry, Euclidean geometry, if you want to do and avoid doing this calculation. The last problem I want to work with is problem 5. I'm going to bring it inside the screen. Now you can see, you can read problem 5. It's here I think it's like me, a college professor never finishes his lecture before the end of the hour and finishes the lecture within 2 minutes after the hour. And let x be the time that elapses between the end of the hour and the end of the lecture. And suppose that the PDF of x has this form. So you see that the PDF here is given with a parameter k, and that doesn't automatically make it a PDF. For f of x to be a PDF, it has to satisfy the properties of the PDF, namely, it has to satisfy that f of x is non-negative, which it does, and it has to satisfy that the integral from negative infinity to infinity is equal to 1. Now, we don't care about satisfying this property, which is part of the definition of the PDF. This one is equal to this, because we are told that the function is the PDF of the random variable x. The only thing we have to see is whether this satisfies these two properties. So let's look at the problem. Problem will tell us immediately that it satisfies number 1. So you have to take k to be non-negative, of course. And then let's look at the integration. So we need the integral from negative infinity to plus infinity of f of x dx. So this is the integral from 0 to 2. If I'm not, 0 to 2 of f of x dx, because otherwise, outside of 0 and 2, the function is equal, the density is equal to 0. And between 0 and 2, this function is equal to kx squared dx, which, if we do, k is a constant, that gives us x cubed over 3 from 0 to 2, and that is equal to k times 2 cube minus 0 cube. So it's 8k over 3. Now, this number has to be equal to 1. So 8k over 3 must be equal to 1, which gives that k is 3 over 8. And we'll call this constant the normalization constant. Why did I set this to be equal to 1? Because I want this equation to be satisfied. So now I have the PDF. So the PDF, f of x, is 8/3, it's 3/8. And 0 otherwise. Now, if you see the presence of x squared, which makes the PDF to take greater values as we approach 2, means that the professor is more likely to go over a minute past the hour, between 1 and 2 minutes past the hour, and and it's not as likely to go between 0 and 1 minute past the hour. Let's calculate some probabilities here. What is the probability that x will go over 3 minutes? That it will stretch the lecture 3 minutes past the hour. Well, this is 1 minus the probability that x will be less than or equal than 3, which is 1 minus the probability that this is the integral from negative infinity all the way to 3 f of x dx. But if you see the maximum value of x for which we have a non-zero value of the density is 2. So this is going to be equal from 1 minus this is equal to 0 because f, the density, is equal to 0 between 2 and 3. Now, that value is equal to 1. Why? Because all the non-zero values of the density are between 0 and 2. Therefore, within the interval 0 and 2, the density has to integrate to 1. So this makes this number equal to 1. So evidently you have 1 minus 1, so it's equal to 0. So it's highly unlikely that you will go 3 minutes past the time, the designated time. Let's look at the problem again. What is the probability that the lecture ends within 1 minute of the end of the hour? So if we are to answer this question, then we have to see this within 1 minute. Then of course would be the probability that will go all the way up to 1. So this is the probability that indeed will go from 0 to 1 minute, and it's 3/8 x squared dx. And let's also put the first, this is 0. I would like to see that. And now if we go from 0 to 1, we have 3/8 x squared dx. So that gives us that's 1/8 if we do the calculation. If you do the calculation that will exceed 1 and will not exceed 2, you will find that this is greater than 1/8. Well, to do this calculation, this is just the integral from 1 to 2 of the density function, and That wouldn't be anything else but that. I invite you to do it to see that this is what I'm saying is true, that this probability is greater than 1/8. So this guy more likely finishes between 1 and 2 minutes. If I ask you, is the median finishing time, is the median X of the extra time the professor uses greater than 1/8, greater than 1? The answer would be yes, this is true, because the probability up to 1, so you see that f sub x, since the probability between that x is less than 1 is 1/8, this is the probability that this is x less than or equal than 1, which is the probability of x is less than 1, and this is 1/8, which is less than 0.5. Well, since f of x at 2 is equal to 1, because we mentioned it, we just mentioned it before, all this is equal to 1. That implies, these two imply, that the median of extra time is between 1 and 2. With this, we conclude today's lecture. Thank you very much. I'm asking you to watch the video CRV's part 2, which talks about the the mathematical expectation of continuous random variables, and it introduces also the normal distribution, which is the next topic that we will do. In the notes that I have uploaded, and we discuss the uniform distribution. The uniform distribution is also discussed at the video continuous random variables part 1. But you don't have to watch all of this. Watch just the first, between around 10 minutes around the 20th minute.